All right, in the last set of videos, I was mainly focused on Wikipedia and doing kind of the basic thing that you always start off with in data science, which is some kind of word count. I shouldn't say data science, more like distributed or large-scale big data computing. And honestly, it's boring. Like, that's not most of your life as a data scientist doing word count. So let's make this more interesting. Let's get a beefier data set. And for that, we've got OpenStreetMap. This is basically Google Maps. They have I think almost every street in the country, actually in the world. And it's a world scale map. It's pretty big. You can download the entire thing because it's open data. So to do that, you go to planet.openstreetmap.org. And this is where my lack of forethought really comes into the picture, because their compressed XML file is 81 gigabytes, and we can't fit that on our VM. I could allocate another disk for it, but it would also take a while to download, and I don't really want to pause making videos today. So what I did instead was I went to academic torrents. And if you're looking for data at all, academic torrents is a really awesome place to go because they have tons of stuff. And I looked for OSM, which is a common abbreviation for OpenStreetMap, and I think that's how, I got to this, North American roads GIS data. It turns out that this is in the wrong format. There's two ways you can download OpenStreetMap data. One is compressed XML, which is what we want, and the other is protobuf, which is a binary format. It's harder to work with, and this is going to load a lot of stuff into memory. So at least I think it will, and I'm not really up to take the risk. So I'm not going to do the torrent, but instead I followed this link to the original download page. And they have a compressed XML file. So that's what I started downloading in Firefox. And that's still going. It'll be going for a while. So this video won't actually include the processing. But it is a good opportunity to talk about what's involved in working with this kind of data set. The reason that OpenStreetMap is interesting is because it's not stored in a very convenient way. And I'll show you what I mean by that. I have OpenStreetMap already downloaded on a server, and I'll just show you what you get. So actually, before I do that, these are LZ4 files. LZ4 is a compression tool optimized for decompression speed. So LZ4-DC OSM planet .lz4 pipe less, and that will show you the text. Okay, you can sudo apt install it, by the way. It's search LZ4. I think it's liblz4-tool is the package name. We'll install it later when we get into stuff. Yeah, here we go. So if you want the LZ4 program, that's the package to install. Anyway, so this is what you get, and the thing that makes this inconvenient is that it's separated into a few top-level sections that don't have boundaries on them, formal boundaries, but they do kind of exist. So we have the OSM root node up here, and then immediately we get a bunch of change sets. This goes on for a long time, and that's kind of the problem, is that it goes on for so long that you can't easily skip past it. Like, it would just take you forever paging through the file. In fact, I think it's like 12 gigs or 20 gigs or something crazy like that of just change sets. So what I did was I split everything out up front. So we have the node XMLs. So gzip dc that, pipe less. So this is after the change sets, then you get nodes. And the nodes are interesting because these are not roads or anything, they're just points. Each point has its own node object. And so when a road is built, it's called a way, and ways refer to multiple nodes by the ID, which means that if you wanted to know the actual coordinates of, say, a road or a boundary of some sort, you would have to dereference it against the nodes table. And that's inconvenient for us because if we ls-lh, we'll see that the nodes table, which I think is still being built, yeah, we're still building it, is already 7 gigs compressed. And I have it in text form, in processed form already. So this one. So just the ID and the latitude and longitude. That is 68 gigabytes as an LZ4 compressed file. So this is a massive amount of data. I think in binary it's like 80 or 100 gigs or something. Obviously, really inconvenient to work with. So that's the first challenge, right? Like, if we wanted to process this file, how would we do the node dereferencing in a way that didn't absolutely kill us on memory or whatever usage? And it turns out that sort is the answer once again. The key to this is to use the Unix join command. I can't use man here, but I can use it here. The join command takes two sorted files and does a Cartesian product join, just like a SQL join. And so what we do is we're going to take the nodes and sort them by ID, which I have here. Actually, these aren't. Are these sorted by ID? I don't think they are. Well, they kind of look like it, but I'm not sure. Anyway, but when we emit them, they will be. So so we can sort the nodes by ID, and then we can take the ways and sort those by the node ID as well. So there's two sort stages involved, if you can picture what's going to happen here. We're going to have the nodes already sorted, and we need to make ways joinable to nodes. So what we're going to do is we're going to reorder the ways table. Oh, actually, before I talk about that, let me just show you what the ways look like. Here we go. So this is what a way looks like. So ways have IDs and then some metadata, which we don't care about, and then they have a list of nodes, which look like this. So we have node ref. And the goal is, of course, to just dereference the node refs. But if you think about the nature of this problem, the challenge is going to be like sorting the ways table by the node ref ID so that we can join it to the nodes table, and then recovering the ways by sorting it back by the way ID. There's a complication in that too, because the ordering of the node references matters in cases of roads or what have you. If you got the wrong ordering, then the road would just kind of jump around unpredictably. So we're going to have to store the ordering along with the node references. And if this all seems crazy and like not typical data science, I mean, we're doing this in a bit of a weird way in the sense that we're just using one computer as opposed to a structured data store or what have you. But a lot of data science does involve this. Like you can't assume that your data is always going to be formatted for you or loaded into SQL or anything like that. In many cases in production, you would never want to decompress your whole data set or do any number of other things that would make your life a lot easier just because the infrastructure is so expensive to do it. So I'm going to take the parsimonious approach here as well and say let's keep this all contained in our VM if humanly possible, and keep all our temp files compressed and all that, and do this in 2 gigs of memory and whatever disk space we have left after downloading this thing. Speaking of which, let's give that a quick check. I need to disable the lock screen. I kind of want to do a video about how to customize Linux to just work for you, because like the defaults they're all right, but they're not super ergonomic. Okay, let's run a terminal. There is a command line tool that will show you free disk space, df-h. H here means the same thing as it does with ls, it just shows you human sizes. So we have 46 gigs of free disk space, and that's with half of this downloaded. So this is going to be another 7 when we commit that. Now, in the family of free disks, there's DU, which is disk usage of a directory. So this means disk usage of temp, human readable and summarized. So let me show you what happens. Okay, DU is disk usage. So if you run it, it'll show you the disk usage of everything beneath where you are recursively, which is sometimes what you want, but often it isn't. So DU-S will show you the disk usage of where you are. And you can specify another directory and it'll just show you what that is. But this number here is, I think, in terms of blocks or sectors or something. And so -H will make it easier. Okay, so yeah, it's in 1K blocks. Yeah, so 562 megabytes. That's actually really good. We're not going to reclaim much. Anyway, so the upshot of all this is that we're going to be processing OpenStreetMap with about I think 40 gigs or something of disk space that we can work with. Yeah, about 40 gigs of free space. And I think we can do it in that because we're only processing North America, which is 14 gigs bzipped. But we'll see. We might run out of disk space and have to allocate a new block device. Anyway, I will do that in the next video when this download is finished, so stay tuned.